Hey, John here. Let's talk about the Verilog always construct. Big shout out and thanks to all the subscribers and thumbs uppers and Patreons, especially the VIPs listed here. Thank you very much for your support. Today we're going to talk about some example programs that can be found in this GitHub repo. The URL right there can be found in the description of the video on YouTube. Click on that, it'll take you here. This always directory right here has a bunch of example programs right here. That's what we're talking about today. Clone this repo down to your PC, and here's the files you're going to end up with. I'm going to go through these one in order from always 0 to always 6. Today we're talking about the always construct in the context of combinational circuits. Always, as a more general concept, is pretty complicated, and this may take a few passes over it in order to fully understand all of what it's capable of doing. All right, so today I'm only going to talk about combinational circuits. I'm going to talk about one kind of an error that's very common that you can run into, and it can be very confusing, so that you have it in the back of your mind if you want to play with this. But we'll get more into the other uses of this later on. So here we go. Let's start with number 0. This isn't actually supposed to be here, but I committed it by mistake. Those are notes to myself for something I got to elaborate on maybe down the road. But if you want to look at them, you're more than welcome. Okay, here we go. One at a time, let's go through these. I got a little README file in here to remind me to make sure I mention all the pieces in here, right? So what do we got? An always block, or what Verilog's specification calls a construct, can be used in a number of different ways. Like I said earlier, what do we got? Here is an example of creating a periodic clock in a combinational circuit. So this is this is just going to be a mess. Just showing you a couple of things, just so you can see what they look like, so you recognize what's going on, all right? We've seen test benches before. We know the difference between a reg and a wire. For those of you that have forgot, a reg is something that you can assign a value to inside of an initial and, or as we'll see now, an always block. A wire is something you don't assign in an initial or an always block. You have to use a continuous assignment in order to assign a value to a wire. And we'll look at more of those as we go to make sure that we kind of understand when to use what in different situations as we go along. All right, so what do we know about these things? The initial block and an always block, which is what I call them and most other people call them as far as I know, other YouTube videos and people I've talked to about writing code in Verilog, we tend to say block, even though the specification calls these constructs. Sorry. Moving on. An initial and an always are identical in every way but one. An initial block will run these items in order as seen from top to bottom, and when it's done, it stops running. An always block, this only has one thing in it, but it will do this, and then it'll go back to the top and do it again and again and again. If I change initial to always right here, what it would do is it would do all these items top to bottom, and then it would come back to the top and do them again and again and again. This is an infinite loop. This is a one and done. That's it. Okay, so in a way you already know how to use an always block. Okay, and on the other hand, not so much. There's a lot of subtle things about it. What do we got going on here? In the initial block, we're going to open up our usual dump file so we can plot this if we want to. We're going to set values to these two variables. We're going to wait a while, and then we're going to stop the simulation. We'll come back and look more closely at this in a minute, because now that we have these things that are endless loops, infinite loops, okay, nothing will stop this simulation. If you want to stop it, someone has to finish it. So that's why we just wait a long time, so that everything in this simulation will run for 100 clock tick cycles and then finish. All right? If you don't do this, you can get stuck. So be careful, make sure that happens. In any top-level test bench, okay, you're going to basically have something that looks like this, probably. In other words, you're going to open up your debugging output dump files. You're going to initialize a bunch of variables. You may do more in here, but as a general rule, you're going to have to wait long enough for whatever it is you're trying to simulate to go through all of its steps and actions. If they're going to be done using always blocks down here like this, you can also direct them by just generating a bunch of signals. I've shown you that in the past. And then finish if you want. But when you're doing it like this, which is much easier in some cases, we'll see, this would be a lot harder to do without them than it is with. So in this case, you just wait long enough for whatever you want to get done, to finish, and then you stop the simulation. Okay? So let's look and see what's going on down here. First of all, again, I said before, I want to make sure that everybody understands this is about simulation. These cannot be synthesized. This code cannot go into a real FPGA. You can't put these delays in a real FPGA. Okay? When we get to the real FPGA and we want a delay, we'll have to create timers and counters and things like that and create a circuit that will do the delay. So don't think you're going to run this code in an FPGA. All right, that's what this is about right there, these comments. Okay, so what is this going to do? Just like I said with the initials all running at the same time, same with the always, because these are identical in every way except in always loops. Okay, so when this is going through its paces, so is this. This is a completely independent block. As is this, as is this. They're all going all the time at the same time, okay? Or at least we are simulating that to be true. And that's a very important point, okay? And it will come up over and over again. Keep it in your mind. Simulation, right? Why? Because you may not have enough CPUs to literally run all these at the same time, okay? So in simulation, they do the best effort they can at faking all these going at the same time. And that is really important down the road as this evolves. Don't learn this incorrectly, all right? I'll try to always beat up this point, especially as we get through the non-blocking assignments, because in simulation, we can't do the same thing you can in an FPGA that has millions of transistors all running at the same time. You just can't. So in simulation, we have to help this simulation along a little bit, and we have to keep in mind the fact that we're not always doing everything all at once, okay? Right now, this is not so important, but it will be very soon, okay? So, what happens here? While these are getting assigned to 0, this thing is running. And the first thing it does is wait, so that's not too bad. We're not actually going to collide and do anything weird here. This also waits even longer. Okay, it's going to wait 11 clock ticks. Then it will proceed to do this. So in this notation is the same as this, by the way. You see what I've got on here quite often, because the alternative is to do this. Yeah, to some degree. All right, I'll do this and leave it in here so we have an example of each kind. END, if I can spell here, okay? Yeah, who wants to type all that garbage in, right? It wastes a lot of space and it can clutter the place up. And this is, in my opinion, easier to read. So if you're going to create a clock, and that's what this is doing, that's going to go on and off and on and off, I tend to do it this way, all right? But these are the same thing. If you have more than one line of code, you have to put it in a begin and an end. And if you don't, you can just list it out like this, okay? So what then are these doing, right? If this just goes over and over and over again, what's it doing? It's going to wait 3 ticks, then it's going to do this assignment. It's going to say clock 3 equals the inverse of clock 3. The tilde is a ones complement, which flips this bit. Remember, it's a single bit variable. So what happens in what order, right? This is going to run, and this is going to run into this delay. And while this is delaying, these will be assigned zeros. So 3 ticks into the reality of this simulation here, this will be 0. Clock 3 will be 0. And tilde clock 3 then would be a 1. So we're going to simply change clock 3 from a 0 to a 1 in this assignment. And because this runs forever, it'll come back up here and wait 3 more ticks, and then flip it back to a 0, wait 3 ticks, flip it back to a 1, and so on. This is a square wave clock. So is this, but they're running at a different speed. That's all. I purposely chose 2 prime numbers so that they don't click at the same time very often. The only time these 2 will click at the same time is when 3 times 11 clock cycles comes by, which is every 33 clock cycles, all right? Which will generate, something interesting, not so much aligned but overlapping clocks, all right? Then I'm going to use those 2 clocks to implement an AND function. All 3 of these variables are type reg you saw up here, okay? So we can assign them values in always blocks. So while these 2 are running simultaneously, this is as well running. So what does this do? The $* means, as I say right here, run once every time anything that is used as an input to any of the assignments or operations or like an if condition or anything at all. If any of those ever changes value, run the body of this always block. This only has 1 line of code, so I don't have to put a begin and an end in there, but I can. A lot of times you see this like this, or you can put them over here, and if you're going to do that, I can put more code in here. Maybe I have a func2, and it has OR in here, and so on. And that's what you'd need to do if you have more than one thing. All right? So I'm going to go ahead and put this back the way it was. This is a one-liner. It's okay to have a carriage return in there. So at star. Okay, that's really all we're going to use today. I'll show you some notes about where this can go awry as we move along, okay? Now, what's going to happen here? If this is an endless loop, and it runs every time this or this changes its value, this is implementing an AND gate, simple combinational circuit, where func is equal to clock 3 and clock 11 at all times. If any of these ever changes the value of 3 or 11, then this will run. I mean, in many ways, you could think of this as a permanently endless loop. I mean, logically speaking, we don't really care. We don't want to care as a programmer. I don't want to care, I should say, that I have to wait until one of these changes before this loop runs, okay? But remember, this whole system of Verilog was created for simulation. And one of the problems with simulation, especially 40 years ago when it was invented, is the cost of CPU time. This thing has to not run super duper slow. So the language itself was designed in such a way that you can hand optimize your simulations. And if you start optimizing, you're going to get yourself into a universe of disastrous difficulty if you're doing it real early on while you're learning. Don't, okay? Just let it go. Say, run this all the time, anything changes, okay? Yeah, you're wasting CPU. Who cares? All right? It will get done, especially these simple, trivial little examples. So let's run this and see what happens. You might say nothing because it never outputted anything. I didn't monitor anything or anything like that. But I have a make plot, which allow us to watch those signals change their values over the course of time if we open up GTK Wave. Go ahead and put these on the screen, and that's what you've got. You've got this thing changing every 3 nanos. If we move the cursor around, let's zoom in a little bit more, you can see this cursor is at 3 nanos. Over here, it's at 6 nanos, right? And this will be 9, and so on. You get a little time bar up here so you can see what's going on. Once you get over to 11 nanos, it's the first time that clock 11 changes, and every time this opens, at least on my system, this stupid thing is hiding all these values, so I got to move this over. So that's what you do. You grab this and move it over, all right? At 11 nanos, you finally see clock 11 go to a 1, and because this is the AND of 3 and 11, the only time this will be high is when clock 3 and clock 11 are both high, right? So you can see them ticking away and the AND gate doing its job. This should be no shock to anyone, okay? But this is just going through the motions to show you what's happening. You can see it in the waveform viewer here, and we can see what the code was intended to do down here with these 3 always blocks. All right. Oops. Let's look at something more interesting here. Here's always 1. README says an always block that implements a decoder. Let's look at what this code does. I got an A, B, C, and I got a Y. I got an initial here that opens up my dump file. I have another initial down here. It doesn't matter that I have 2. They all run in parallel at the same time. And until one of them waits, all these items here will go in the same time unit. And the simulator will try to make it appear as if all that happens at once, to the best that it can, okay? And it's not until you get here that anything actually waits, okay? So that'll be done, and all this will be done, and before this initial block waits. And it'll only just do more stuff, wait, as it goes. Down here we have an always block. This one's got to begin because we got a lot more going on. We can use it if then. We can ask all kinds of questions. We can do all kinds of fun stuff down in here. Now, I'm talking about Verilog, and System Verilog is the, second version, right? You got Verilog, and they have these dates like Verilog 2005, Verilog, I think there was a 1995, and so on. And the years were its versions. And for some reason, rather than incrementing the version by putting a new year on it, they just renamed it System Verilog, which is really like Verilog 2008, I think. Yeah, correct me if I'm wrong, whatever year System Verilog, the first spec of that came out. And I bring that up in this context because as you wander around, you see Verilog, you'll see System Verilog. What's the difference? They're all the same thing. System Verilog is the newer release. And it has newer things you can do that you cannot do in the older Verilog release. And I'm wasting your time talking about it right now because what we have here are examples of old style and new style ways of specifying things. When you wander around on the internet looking for Verilog code, or even System Verilog code, because it is, as defined in the spec, a formal superset of Verilog, anything you write in Verilog is going to run in System Verilog, but not the other way around. This is why I want to make sure that we all understand Verilog before we move on to System Verilog, if at all, okay? There are certain really useful things that System Verilog provides to help you get warnings and stuff about things that you might have done wrong. Massive, wonderful motivation to advance the language, to check more stuff, to help the programmer not have a problem, okay? But it's really important that you understand what has happened and how it evolves, at least in my opinion, so that you know how to use those new features, and you know when you see some code, how do I want to think about this and what could go wrong, okay? Otherwise, you're going to just waste tons of time debugging your code. So what do I got here? I got a bunch of commented out things that all do the same thing. We've seen always at star. This is technically called a sensitivity list. I am sensitive to the entire world. Anything changes that matters, okay, to this code, and by that they mean any inputs, in this case A, B, and C, okay? If it matters to me, run it. Now, when we get down to these versions down here, this is the old way. If A changes or B changes or C, I hate this notation. As I say, ew, yick. This is what you had to do in the dark ages, okay? At least get this stupid word out of there and change it into a comma. A, B, and C. If any of those change, because they're on the right-hand side of an assignment, or they are in a condition of, some sort of an input of any kind in the block, then run the block, okay? Now, if you try to name them all every time, and you forget one, you're going to have a problem. And one of the motives to forget one is to provide you, the programmer, a way to optimize the simulation if you just happen to know that this always block doesn't need to run when, for example, maybe you don't care when C changes, even though you use it down here. You might not really care. And you might not want to have to waste your time in maybe having this run so many times. It may take days and days, and I'm not exaggerating, to simulate some more interesting and complicated circuits. So that one benefit of being able to use this notation and not say just do it all the time is to say do it when I happen to know it's important to do it. But this is incredibly error prone when you are trying to create a simple combinational circuit. We'll see why in a minute. Don't do this crap. When you're trying to do a combinational circuit, use this or this. Basically, the parentheses here, when you put the asterisk, are optional, but I feel that is kind of subtle. I don't generally use that. I use this. Don't always put the spaces in there, but I want it a little more visible. Anyway, so that's what's going on with that. If you download code and you see all these variations, that's what they all mean. No, I don't like this. I never did. It's like, who invented this thing? The designer of COBOL? Moving on. Okay, so all the time, do this over and over and over and over again. So what is a decoder, right? If I want a 3-in, 8-out decoder like a 74LS138, there's your implementation in Verilog. If A, B, and C, these inputs, this is the most significant bit, this is the least significant bit. If you really wanted to do it in a 74 138, these letters are in the wrong order, but you know what I mean, okay? So you got a 3-bit number. If you got a 000 in binary, then I want to output this. This is the 0th output. If I got a 001 in binary, right, that would be a 1. These are decimal values. If this 3-bit ABC concatenation is 1, then I'll put the 1-bit and so on. And this classic diagonal from a decoder. We've all seen this. If you don't know what I'm talking about, go ahead and Google, find yourself the spec sheet for a 74LS138 and read this spec sheet. You'll see this exact diagram in its truth table, okay? All right, so what's going to happen? Let's look and see what's going on up here. Over the course of time, these reg variables, right, are going to be assigned values. You got a 0, and then you got a 1, and a 2, and a 3. So what we should see, and of course a finish down there, is we should see it go through this. It should see output that, and that, and so on, right? We also have a monitor saying at time such and so, here's the 3 address bits, and here is the Y value expressed in binary. And that's exactly what we got. Address 000 all the way up through 111. You see the classic diagonal. Everything's great. The world's fine. We're done. End the video. Not quite. Not so fast. What happens when we make mistakes? There's some subtle things going on in here. Same exact program. We got the same counting going on in here. The finish. What happens if I screw up and I miss one of these? What happens? This is a huge problem. A very easy mistake to make. And in this case, it's kind of obvious, but you're not always going to build yourself a 74LS138. You're building nasty, complicated things with tons of inputs, and it's very easy to miss one. Oops, I forgot to assign a value. What happens? If you look in here, if you build an always block like this that you intend to be combinational and you forget to assign a value, you optionally assign it, like I did in this mistake version here, then what happens is you get what's called an implied latch. And in Verilog, depending on your compiler and your settings and things, you know, the compiler could tell you blew it. but it doesn't. And even if it does, it doesn't consider it an error. This is a feature of the language. And then there are times where you do need to do this, okay, in order to get what you want out of it. But if you're trying to design a combinational circuit, these so-called implied latch situations, and I'll explain why that's called that in a minute, are a big pain in the butt, okay? This is why System Verilog decided to suggest against using always. System Verilog has an always underscore COMB for always combinational. If I call this an always com in, or a comb, depending on how you want to say it, like this, and this was compiled with System Verilog, and I gave it this, it would generate a warning or an error because this is not a combinational circuit. It can't be done. Okay? And we'll explain more about that. And System Verilog would say, you know, if you really want to do this, you can't do it with an always combo. You have to do an always latch because you have to have a stateful circuit if you're going to do this. Okay? Oops. It also has to be spelled correctly. All right? But in regular old Verilog, they didn't have those things. So, a newbie just getting in right now might say, don't even look at old Verilog. Well, the problem is you're always going to be looking at old Verilog, and unless you understand old Verilog, you can't use any of the existing code that's floating around, and you're not really going to have a really internalized understanding of always latch versus combo versus flip-flop, which is another kind, okay? So the three generally used always block styles of code design in synthesized circuits have their own three separate names in System Verilog. In regular old Verilog, they expect you to have your big boy pants on and just know what you're doing, okay? Not always the best idea, but that's what you get, okay? Less help. That's what's going on here, all right? This is, to me, the number one biggest difference that affects me personally and is useful when I use System Verilog over regular Verilog, okay? This has been out for about, 15 years now, System Verilog, and there's still a lot of people still doing the old style Verilog, okay? So, again, you really need to understand the oldie-timey because you will run into it, guaranteed. You do not want to ignore this, okay? You need to have an understanding of it. So that's why I'm focusing on it. Moving on. What does this thing do? If I don't assign a value to y is not supposed to change. That's why we need a latch. So what happens here? When A and B and C have all these different values, we simply assign the right value to the output of the decoder. We go on our merry way. As soon as A, B, and C equals 6, or in binary 1, 1, 0, there's nothing that it's supposed to do, and Y should be left alone. If then the A, B, and C values change from that to 0, 1, 1, which is a 3 in binary, it should change to this. So what has to happen is the circuit and the simulator have to figure out a way to build this as a circuit that has a latch in it that is implied by the fact that I don't always give a value to this thing. It has to stay what it was before, even though we run into this case right here. So let's see what happens. 1, 2, 3, 4, 5, 6, 7. And in case number 6, notice that this value is the same value it had before when it was 5. This is so subtle and such a giant pain in the butt that when you're designing and you're debugging and you're verifying, you want to create a test bench for your circuit. This is why you need to create very good test benches and check your results all the time. This is not easy to see, is it? No, it is not. Let's look at some other ideas on how to improve our odds of not sucking when we make mistakes, or at least be able to fix them when we do suck, okay? All right, here's the same thing again. Oops, let's take a look, see at the README. Blah, 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 blah. What do we got in here? It also has a default value. There we go. This is use default or an else to propagate something that is in my circuit, so it is less likely to go unnoticed in the event that there is, in fact, a problem. All right, here's one way to do that. We can just have an if else, 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 else. Well, what if none of these match? Well, then assign it all X's. Now, this can be synthesized because X is being used as an output value. In synthesis, there is no X inputs, okay? It can't be unknown. In reality, everything has a real value. So there are no X inputs, but X means I don't care. You can do anything you want, okay? But in simulation, X is real obvious. Because now when we run this, and we have this bad case, it won't just say, oh, I'm going to just leave 5 on there because that's what I had before, because I'm counting 1, 2, 3, 4, 5, 6 like this. It'll leap over to these X's and it'll stick out like a sore thumb right in your face and go blammo. I don't know what to do here. And I designed this into my code from the onset. Okay? Now there's another way to do this, like this. And I hear some people griping about this. So, oh, that's not hardware-like. I don't care. Neither is writing code that looks like C that's supposed to mysteriously materialize on an FPGA. All right, so what's going on here? What's the difference? Well, if you put it on here, I can make all the mistakes. I can comment all these out. I can have a whole bunch of missing ones. It doesn't matter. I could make a colossal screw up, and at least what happens is I always have a value assigned to Y no matter what. And I am strategically selecting a value that I can identify in my test case that'll shove itself in my face real big, and I don't have to do it right. I don't have to remember that, oh, I need to put an extra else down here, and this is, again, so trivial. An idiot should be able to do this and put an else in here, but it's not so simple. These things get very complicated. You could have 17 levels of nested if then else's in here and all kinds of other stuff going along, and it may not be obvious when you do something more realistic. So I tend to use this technique where I pre-assign them up here, and then I replace them with the code down here that I hope was done correctly. Now, this does not mean that the value of Y is going to glitch when this code runs. Because in Verilog, what happens is, with the if-else is and all this other stuff, this doesn't take any longer to execute this down here than it does to do this one here, because the FPGA doesn't really go in here and check and check and check and check and have go-tos and jump statements and all. That's not what happens in a real piece of hardware. Now, the simulator might do that, but the real hardware doesn't. It'll build a decoder with gates, okay? And I stress this point because what it's going to do is it's going to say, when A, B, and C are zeros, I'm going to output this. Period. It's going to do that because even although I have a default value, I assign a value, my intention is to have a default. Okay? The FPGA won't do this if it says I really need, what is the end result is what it looks at. I'll start with this, and then later on I'm going to replace it with that. Therefore, I really need to output this when A, B, and C are all zeros. It'll go straight there, it'll output that value, and it's done. So in other words, it won't set it to garbage and then 1. Okay? So you don't have to put the else down here. I view this as much easier to see what's going on. So let's go ahead and make this mistake and run it again. You can clearly see that it's doing the same thing. And we can also then, the benefit of this is if I make more than one mistake, granted else in this particular example would still do the right thing. So even if I have these two mistakes, right? But it's not what, that's not my point. My point is, when this is ugly down here and very complicated, and it will get there very soon, you don't have the luxury of always knowing that everything's perfect all the time. So I tend to put these in a place like that rather than putting them down here. But either way works. It'll do the right thing. Let's move on. Here we go. What is this one? Remember that double equals is comparing them literally. More reasons that you want to have a default. Okay, so here's another thing. What happens in simulation if one of the inputs is X? What happens? All right, look what I got going on down here. I've got, we're going to go through 0 through 7 just like before, okay? Then down here we're going to get to... we're going to set input B to an X, so we'll end up with, after this, it'll be a 1, X, 1 in ABC order. Then I'm going to put it back to a 1, so it'll be back to 7. Then I wait, and then I'm going to assign them to a 0. Then I'm going to make it an X, and then I'm going to put a Z in there. I'm going to just send garbage into this thing. What's going on, right? Well, if we go back to our original design, what's going to happen is, if any of these is X or Z during simulation, it cannot match any of these values. So you end up down here with, I don't know what to put in Y, and you now have an implied latch all over again. So let's look at this one. We go through it normally and do the right thing. Thank you very much. We put garbage in there. It doesn't know what to do. It's going to say, keep the same value it had before using an implied latch. We go back to all ones. It knows what to do because that makes sense. It goes to all zeros. It knows what to do. That makes sense. We then put garbage. I don't know what to do. I'll just keep the last value in the latch. What if it's floating? Same thing. Now, I added this one because, look, 1 unknown 1 is outputting that value right there. And up here, 1 unknown 1 outputs a completely different value. This is the absolute hallmark of a circuit that is not combinational. It is stateful in that the value of Y depends on what it was before in both of these two cases. All right? In fact, it does here too, but that's beside the point right now. I have the same input with different outputs because of what happened before, okay? This is not a combinational circuit, and these are easy mistakes to make, okay? So always include yourself a nice default case. I think that's what I'm doing in the next example. So no need to wreck that one. La 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 la. We got a couple of things we're dorking around. It's not quite the exact same example, but we're messing around. What did I do? I put the else in down here. That's all. So if you make this one, you can see that when we have unknown cases that cannot match with X's and Z's, we're outputting all X's. Okay? So in a simulation, I do this because I do, what are we going to make? Plot. I look at these plots when you get, I mean, this is not a particularly interesting example, but when they get interesting, I oftentimes find myself, I need to look at these plots. Look at these big red suckers there, okay? That means these are when it's unknown, all right? Again, I can't see too well here, but if we put the cursor on here, we say B is X, and all the outputs are X's. So it makes it red, okay? That's what I want to see when the output's unknown. See this yellow line right here? That's when this value is a Z, at least in this plotting tool. Different plotting tools could do different things, but they really stick out, okay? So what I try to do, think about what's going on here. When I want to test a circuit, when I design a circuit to be tested, you definitely want to make sure that you cover these bases. Even if you're going to use system Verilog and you're going to use an always COM, it doesn't matter. Put these extra covered cases in here so that you can see them sticking out like a sore thumb when you're trying to debug. All right, here's the classic example that everybody always does, the 7-second LED decoder. And if you do a Google search on 7-segment LEDs, you get all kinds of pictures and diagrams and blah, 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 blah. Hi, look, Jameco. Look at these. I want you to see this because they always letter them the same way. You got an A, B, C, D, E, F, G around in a circle like this, and G is the middle one there, okay? So when you want to put numbers on a 7-segment LED, you would say, I want, like the number 1, you would have B and C turned on. If you got a 0, it'll be A, B, C, D, E, F, and G will be off, right? A 3 would be A, B, G, C, D, with F and E off. All right, I mean, we've all seen LEDs, I hope, before, right? So what I want to do is build a 7-segment LED decoder. And here it is. I've created a module that has its 7 outputs, and I've called them A, B, C, D, E, F, G to match the diagram you just looked at. You can find just about any diagram anywhere of a 7-segment LED, and it'll letter them, and this will be the order that they're lettered. I have to have a 4-bit input, and I'm not going to do a decimal one. I think decimal is utterly worthless when you're dealing with 4-bit Boolean binary values. Give me a hex decoder, okay? For crying out loud. Decimal is not interesting. It is interesting, I suppose, because as an example of don't care situations, because in decimal, you don't really care what's on the LED when you have these combinations down here of your inputs, A, B, C, D, E, and F, in a 4-bit binary number. You're not supposed to have those if you want a decimal display, okay? All right, what am I doing here? I'm playing some games with stuff that we already talked about. Notice my inputs and outputs are all wires right here. Because I have a decoder and I want to assign the output a value, and I want to do it, in this case, in an always block, that's a combinational circuit, I can't assign this to a wire. Now, I could assign all these outputs to be, or I could define them all as regs if I wanted to. And I could put this big curly thingy like this in down here and say A, B, C, D, E, F, G in curlies equals this. Okay. Or I can say, all right, here's a reg, a 7-bit vector called segs. And at any time, I'm going to use a continuous assignment that says connect the segs in my circuit such that it drives all these outputs. Okay. Now, segs is not a register. It's not a latch. Okay. This is just the way they decided to define the variables in Verilog. We've seen this before. A wire is something you have to assign a value to outside of an always block. And if you're going to assign a value inside an always block, it's supposed to be a reg. In System Verilog, they add new data types like logical and stuff like that. Okay. But again, if you look at any code that's more than a decade old, and there's a ton of it out there on the internet, you're going to see regs and wires. Okay? Newer stuff will use other types. That's fine. But we're going to do it this way. So what's the point? When I assign a value to segs, I'm really driving these wires. It's not going to be a real latch. Because I'm handling all these cases, it'll optimize the latch away when I compile this. It could be a latch if I screw up and leave one of these out. Now it's now it would be have to use a latch, but now it just uses gates, okay? For reasons we just talked about. Okay, so what do we got? This even has an enable input. If it's enabled, do this. Otherwise, if it's not enabled, we can just simply make them all float. Or we could put them all to zeros, or we could put them all X's, whatever we want, okay? Of course, if you're going to say enable, usually that means to turn on the LED. So to shut it off, we probably want to set it to 0, or we want to let the wires float by setting it to Z, which is physically disconnected, okay? So here's how this thing works. We've already seen most of this, except for the enable. So now I have this nested if in here, and I got all these cases, 0 through F, and these are all the bit patterns. I just did them in my head. We know this is A, B, C, D, E, F, G. We know that O, or 0, is all the way around the outside. We know the G is the middle, so we got A, B, C, D, E, F on and G off. What's a 1? A is the top, so it's off. B and C are down the right side. Those are on, and all the rest are off, and so on. This is not that hard to do in your head. If you can't do it, go ahead, draw this up, put together a truth table and columns labeled A through G, and work it out, okay? That's what you're going to end up with. Now, if I end up in a situation where D has unknown values or is floating during simulation, which will never happen during synthesis, but during simulation, I want to know if there's a problem somewhere else. And I guess I didn't punch that hard enough before, or even at all. In my test bench, I could have an error in my test bench, and that is what this is going to indicate. If something outside of this module sends unknown value X's and Z's on the bits that represent my D input here, this module will set all the outputs to X, so that again I can see them easy in simulation. All right, let's look at the test bench for that module. That module is synthesizable. I'll leave it as a task to the viewer to actually create a top level synthesizable module and hook it up on your eval board. We'll do that later on this channel, but this is getting long. This video is getting long as it is. We'll hook it up to a real FPGA some other time. What are we going to do in here? Test bench. We got an enable signal. We got data. We have the 7 segments, and now I have an integer variable because I'm going to use a for loop to count from 0 to 16 rather than just hard code all those lines of code. And the reason I'm going to do that is because we're going to actually generate a little picture of what the 7-segment LED might actually look like with all the different values. Now, we've kind of seen these before. The LED is the name of the module that holds the 7-segment decoder. UUT is the name of the variable or the construct in this module. I could have just easily called it ZZZZZ, okay? This is the name of the thing I'm creating. In a lot of ways, it's like defining a new object or a instance of a class or something. This is an instance of a module called LED, and I called it all Z's, or I call it UUT, or DUT, very common name for a variable in a test bench because that is the unit under test. And for each one of the ports, I have to connect them. These are the names in the LED module. These, in the parentheses here, are the matching names in the module that instantiates the LED over here, right? So I got my EN is called EN, I got a D and so on, and then I got an ABCD. These are all named the same, but this one actually has a different name. I did that on purpose just so that we can see this as another example of how you're connecting the ports together. Okay, so this is an input and this is an input inside the LED module, and all these are outputs from the LED module, and you got to be a little bit careful what you hook your outputs up to. Remember, this cannot be a register because I'm not assigning it a value in an initial or an always block. What's coming out of this module, even if it's assigned down in there, in an always block down there, it doesn't matter. It comes out as a wire. So the outputs of an instantiated module, you want to connect them to a wire. Okay, that's just a Verilogism. All right, so what am I going to do? I'm going to throw a monitor on there, open up my usual dump file. I'm going to turn the enable signal on. I use active true logic almost all the time in all my modules and stuff in my Verilog. Why the hell would I use active low and all this confusing? I got to remember all this crap in my head. I use the active low stuff on the outputs and the inputs of the physical pins of the FPGA for the external world as needed. And which is fine out there, but inside I like to think of myself as a positive guy. I try to use active high logic so that I don't have to do too many gymnastics in my brain all the time while looking at my code. This is commented out. We'll look at that in a minute. What am I going to do? I'm going to use my integer variable. For loops don't exist for real Z's and FPGAs. What this really is doing is it's a code generator. It's like a fancy macro is what's really happening in here. And it says replicate this code over and over and over 16 times. That's really what happens in a for loop. There's no iteration after it's compiled. Okay? You literally have this unrolled loop of D equals 0 followed by a wait. D equals 1, wait. D equals 2, wait. And that's what then runs. Okay? Be careful. We'll come back to for loops sometime down the road and see why this is true. Do not think this is iterating when the circuit is created. All right. Now, of course, this is not synthesizable anyway, but we're going to go ahead and display this as using asterisks and draw kind of an LED on the screen and when we run it in a minute. So when it's done doing all 16, it'll wait. It will set one of the input bits to an X. I want to test this thing. What happens if my LED gets crap data, an unknown value during simulation? Is it going to screw up or not? And make sure that I can recognize that it's not doing something weird and getting stuck in some screwball state because I blew it and didn't make a proper combinational circuit. I'm going to then disable it, and then I'm going to go ahead and put some more data in there. So here we go. It's a lot like the other one, except we're not decoding, just 1, 2, 3, 4, 5, 6, 7, 8, like a 74LS138. We got all the kinds of crazy patterns that are more useful for lighting up LED segments. So we have the enable on, and then we have the enable off. We just saw that. We see the for loop that expands out into all that code that we talked about, or all the circuitry, I should say, going from 0 to F. And in all cases, we see it has something coming out of it. I can recognize that's the 0 and that's the 1. 3, what is that? That's the A, B, C, D, because A is across the top, B, C on the side, D on the bottom. E and F should be off, which is these, and G should be on. That's the middle prongy thing in the middle of the 3. So that looks good, and so on. A 7 should also be 3 on and the rest off. Yes. Why? Because A is the top, B, C is the side, and all the other ones are off. So a quick spot check, and 8 is an obvious one as well. All of them on, all right? Okay, that all looks good. So what happened here? Down there, D has one or more of the bits. Remember, I set to X. What does my module do? It has an else in that case that says put all the outputs to X's. All right? So this is me propagating a real big, obvious, recognizable thing and shoving it in my face when I'm trying to evaluate what's going on. If I disable it, remember, the code said, I had a couple of comments in there. What did I do? LED.V. I set it to a Z if it's disabled. I'm disconnecting myself from the LED. And that's exactly what happens here. If I then, even if I have it enabled, both states here, enabled in garbage unknown values on my D, I get the Z's because it's disabled. That takes precedence over the fact that the decoder slammed out these X's, right? Because the enable, why? Because I have a priority encoder in there, and we talked about that before. Because the checking of the enable takes precedence over the checking of all the input values. This is a great example of a priority encoder, okay? Here we go. Here we go. Let's edit this now and comment this back in. Now, I had it off because it's going to spew a lot of junk on the screen. Let's see what this thing does real quick here. I want to print a string whose value is what? If A is true, I'm going to print some asterisks. Otherwise, I'm not going to print anything at all. I'm going to print a bunch of spaces. And then I'm going to come down here, and I got two. So you can sort of see what's going on. You can sort of see the LED here. A is the top. F is the upper left, and B is the upper right. So what's going to happen is I'm going to have, what am I going to do? I'm going to have one row of asterisks on the top that's be all asterisks or spaces if A is on or off. And then I have to do the left and right at the same time because they're on the same, horizontal thing. So if F is on, I want asterisks on the left side. Otherwise, I want a space over there. followed by some spaces, and then if B is on, I want an asterisk on the right side, and so on down the line here. I'll leave it as a task to the viewer to figure out if they want to take that further and understand more about what's getting displayed. But if we scroll back to the top here, you can sort of see this. If I kind of like back up far enough and see this giant O, there's a big gap in here because the way I printed it, the horizontal asterisks in here would consume that space. But that's your 0. There's your 1, there's a 2, there's a 3, there's a 4, there's a 5, and so on. 6, 7, 8, 9. A, your B looks like this. C, D, E, and F. Just the way I decided to represent those particular values. So now you see how you can create a test bench that not only kind of like checks the stuff, prints it out, we can run it through the plotter. This is not so useful, in my opinion, to see if this works, because it was easier to see when we actually printed out the asterisks on the screen, but you might need to use this if you have something else weird going on and you want to check the invalid states like over here. I can't, this is not so easy for me to say, oh, that's clearly a whatever, an 8 or a 9. Okay, that's a toughie. And again, it opened it up in a way that I can't see the 1s and 0s, okay? Anyway, you got all these different ways of looking at the stuff. You pick the one that's most appropriate for the situation you're in. So, this has gone a bit long. We'll pick up more about the always block next time, and we'll look at latches, and we'll look at the blocking and non-blocking assignment differences and why they exist. Spoiler alert, it's all about simulation again, okay? It turns out that synthesis doesn't really care about those differences. But when it comes to these blocking and non-blocking, Google it around, read some documentation out there. I'll give you my spiel on it. Everybody else has a different way of looking at it. But in the end, if whoever is telling you how they work and they don't mention that it is all about simulation, then be very careful about what you're trying to learn from that source, okay? They may not be wrong, but it really only applies to simulation. It does not rear its head so much so in synthesis. So be very careful there, all right? Again, I want to make sure that we all understand where these lines are between simulation and synthesis. Thanks for watching. I'll see you next time.